I hope everyone's doing well. I am Mr. Ish. Thank you for joining me. For this video, we're looking at a very interesting outcome or a trend or a pattern that develops with infinite geometric series that are convergent. As a very quick example, what is a convergent infinite geometric series? Look right over here. I'm looking at something which is 1 over 4 to the power of n, but other examples are 1 over 2 to the power of n, 1 over 3 to the power of n. Any value over here where you're looking at a base constant which is larger than 1, it will be convergent. When you expand this out, what will you have? 1 over 4 to the power of 0 plus 1 over 4 to the power of 1 plus 1 over 4 square plus 1 over 4 cube, on and on. You know, if you want to find the sum of the series, you have to find the common ratio, but I'm telling you a quick shortcut. Whatever rule you see here, the fraction, ignore the exponent. The fraction is always your common ratio, and it will always be the case. Pick any of these two, 1 and the one before, you'll have your common ratio equal to exactly what you see over here. 1 over 4 square, which is a 1 over 16, divided by 1 over 4. Common ratio here will be a 4 over 16, which is 1 over 4. Exactly what you see over here is your common ratio. What is an interesting aspect of this common ratio? When the common ratio is less than 1, it's convergent. When it's equal to 1 or larger than 1, it's not convergent. But here we're clearly less than 1, it's convergent. What's our sum of series over here? The infinite sum of this series, it will be this formula, the a first term divided by 1 minus r. What's my a first term? For these type of convergent infinite geometric series, the a first term is always equal to 1 because it's 1 divided by some constant to the power of 0. It will be here 1 divided by 1 minus 1 over 4, 1 over 3 over 4, and you're getting a 4 over 3. But notice the sum, it's a very finite value, but there's a specific aspect with regards to these infinite geometric series where you focus in terms of your pattern and your trend recognition with regards to the sum you receive. And what is that pattern? As this value right over here, I'll call that a, because your rule would be 1 over a to the power of n, and you're looking at it in terms of a sum from 0 up to infinity. As this a value gets increasingly large, this sum of that specific infinite geometric series will become closer and closer to the value of 1, or you can say it will become closer and closer to the value of your a1 term. And I'm going to show you that. What will be your a1 term? It will always be 1 over a to the power of 0, which will be a 1. And let's show that to you to be the case. And that right there is a pattern or the trend that I am talking about with regards to the theme for this video. You have a rule, and we're going to rewrite it over here. N equals 0 up to infinity. We have 1 over a to the power of n. The specific aspect of this trend is that the a value over here, the base constant, must be larger than 1. It cannot be equal to 1, because if it were, your entire series would be 1 plus 1 plus 1 plus 1 infinity times, and it's no longer convergent, because in that case your common ratio will be equal to 1. That creates divergence and not convergence. When your a value here is larger than 1, like 2, 3, 5, 100, 1000, a million, then you have this specific trend develop, and that's what we're talking about. I told you the common ratio here is exactly what you see. It'll be 1 over a. The sum of the series in terms of infinity will be your a1 term divided by 1 minus 1 over a, which is your common ratio. And what will this be? What's your a1 term for all of these? It's always 1 divided by something to the power of 0, and it'll be 1, but I won't write it out like that. I'll just keep it as a1. You do the fraction algebra, a minus 1 over a, and what are you getting? a1 times a divided by a minus 1. That's what you're getting. And now think about it. Put a specific value here in terms of a very large value, and see exactly what you get. If I'm looking at a rule which looks like this, and I'm picking a value here of 1000, in essence I'm saying I'm looking at a rule 1 over 1000 to the power of n. It'll be an infinite geometric series when you expand it out, but this is what I have. Now if I were to look at something like this, what will my sum of this series be? I have the formula right here. I know my first term will be 1 over 1000 to the power of n, which is 0. It'll be a 1. 1 times 1000, because I'm using here a value of 1000, divided by 1000 minus 1, which is a minus 1, it'll be 999. I'm getting 1000 divided by 999. You run that on your calculator, well, you get 1000 divided by 999. I'm getting 1.001. I'm getting close to 1. Increasingly close to 1. What if supposedly for the purposes of this video, this a over here was 5000? Now in this particular case, I can do everything here. I know my a1 term will still be a 1, because it will be 1 over 5000 to the power of 0 will be a 1. And here I'll put 5000, and here I'll put 4999, because it's always a minus 1. And now we run this through, and what will we get? 5,000 divided by 4,999. I'm getting an even increasingly close number to the value of 1. So that right there is the essence of this video. I'm showing you for this infinite geometric series trend, for a rule which looks like this, it's convergent because the common ratio is less than 1. As this base constant becomes larger and larger than 1, your entire sum of series, infinite geometric series, will become or tend towards the value or the sum of 1, and that'll be it. It'll be entirely dependent only on the first one, because everything else out there will be negligibly small and irrelevant. Your entire sum will become equivalent to exactly your first term, as you're kind of seeing right over here. Your first term will dictate that entire sum. And that's it for this video. Thank you. Have a good day.